Another interesting application of interference pattern is that you can get an interference pattern not just with a single shift, but you get with multiple shifts. And the interesting other thing is you can get interference patterns in ways that you didn't really think. For example, physicist Thomas Young was studying waves, and he actually did something with light waves that had previously been done by Christian Huygens quite a number of years earlier. Because remember, Huygens introduced the idea of wave properties and studied waves, and he thought he could explain light as waves. And most people quit thinking about light as waves once Isaac Newton successfully started talking about particles and particle motion. And he actually derived a whole series of optics lectures on the idea that light might be made of particles. Waves became more interesting in terms of light back when they got back to Maxwell and his discovery of the wave equation of light. So if you think about it, if you had two slits of light here, and you have waves, coherent lights, all these waves are in sync with each other in here, and it goes to these two slits. Now, what you might think is you would get two bright spots over here as the light goes through. And this is the classic sort of explanation. You'd expect that sort of thing. That's what you would have gotten if you looked at Isaac Newton's work, light as particles. But that's not what would happen if light's a wave. Because Huygens says that each little piece of the wave is like a source of waves. And so at each little slit, the waves are going to spread out this way. So rather than just going straight, they would also go at angles. And so what would happen is light from one slit would come here, light from the other slit would go to that same spot. And so then they would interfere. All the light was in sync to begin with, but the light would then have to go a different distance right here. And so Young realized that would mean you would get interference patterns over here. So what would that look like? So you have light coming in here, and the light has a certain wavelength, lambda to it, hits these slits right here. The slits are some separation d here. So there's some separation d away from each other. And then we have some kind of screen over here that the light runs into. And so you imagine a line going straight this way. And he says, well, light is going to be right here. So you'd actually get a bright spot dead center between these two, where classically you get nothing, you'd actually get a bright spot right there. And then he said, well, you get another bright spot up here, because what happens is one beam of light goes one distance, the other beam of light goes a different distance. In between, you get a dark spot. Why a dark spot? Well, because now we have this difference in distance right here. So some little difference, delta x, that the light traveled. Well, if you draw a line up here, the angle between straight on and that spot up here is theta. So this is going to be theta right there. So delta x is going to be d sine theta. If d sine theta, so if delta x equals half a wavelength, or 3/2 wavelength, or 5/2 wavelength, then that is going to be destructive interference. If delta x is 0, or a wavelength, or 2 wavelengths, or 3 wavelengths, that's going to be constructive interference. So that means you're going to shift it a little bit in the middle, bright spot, then dark, because now we got destructive interference. The path length is half of a wavelength. Then you get constructive interference. The path length is one wavelength. Then destructive interference. The path length is 3/2 of a wavelength. Then constructive interference. The path length is 2 wavelengths, and so forth. So it would alternate bright, dark, bright, dark. Okay. And so this bright, dark pattern. Okay, we could say we have bright, okay, that's going to be constructive interference. That's going to occur whenever the path length, okay, that's d sine theta, if that is equal to some integer times the wavelength, where the integer is 0, 1, 2, 3, etc. It's going to be dark, so that's going to be destructive interference. That's going to be when delta x, that's our d sine theta, that's equal to m plus 1/2 lambda. Okay, so again, m is going to be 0, 1, 2, 3, and so forth. Okay, so now we have the conditions for constructive or destructive. So where you have a bright spot or you have a dim spot. And so Huygens had already done this sort of thing. Huygens had done the experiment many, many years earlier, having what today we refer to as a wave tank, and that's just a tank of water that waves are moving across, and they'd hit these two openings, and they'd spread out the openings, and you'd end up on the far side big waves, and then regions in which there was like calm, no waves. And so Thomas Young replicated this experiment by having a coherent light source of some sort. Today we use a laser to do that, though he did not have that option when he was doing it. But we would use a laser today for coherent light source, and on the screen over here you would get these interference patterns. The interference pattern with the bright spots, and we call them, and we actually have a term called a fringe. The bright fringes, that's the bright spots there. Those bright spots are going to be, or the bright lines there, they are going to be where we have constructive interference. So the d sine theta is equal to m times lambda. And so this is the basic idea of how interference patterns work. And so we'll do an example using this.